Hello everyone, my name is Jorge Reyes and I am a GA with the Department of Mathematical Sciences, and my talk is about improvements on developing novel Ramanujan type identities. So here's just a quick outline. I'm going to talk about the motivation, established methods or what's currently being done, novel methods, which is what we're doing, and then a concluding remark, okay? And so mathematics is a really wide field, right? We have things like number theory, which have applications to CS or cryptography. And then we have PDEs, which can be applied to any field of engineering pretty much, or physics. And so just to kind of talk about where we're going to be in math, it was really all inspired by this guy, Srinivasa Ramanujan, who is really kind of like a mathematical rock star. Okay, he's one of the most famous mathematicians in all of history, and that's because he made a great impact on several branches. Okay, so he didn't just stick to one field; he really connected some fields together, and he has nearly 3,900 results. All right, which is a lot for anyone. And if anyone's ever seen this movie, The Man Who Knew Infinity, it's actually a documentary about him. Okay, highly recommend. And so the work we're doing is based on Wong, a 2021 paper involving what we call Ramanujan type identities. Okay, and so Ramanujan in his work came up with these identities. Okay, which is really kind of like a mathematical artwork. Okay, I don't have a lot of time to explain, but the left hand side here, we have trig functions, right? We have cosine, and this is called transcendental also. And when you have them like this, they equal this right hand side, okay? Which, if you notice, doesn't have any trig functions anymore. And so this is really strange, all right, and interesting to mathematicians, because we found a way to get rid of this transcendental function and get back to algebra, which is something that we're more comfortable with, okay? And so Wong decided to be interested in making new ones and how to make them, okay? So here's just a couple of new Ramanujan type identities that Wong and other collaborators worked on. And in particular, we're going to talk about equation 1 here. So this one with the signs, okay? I'm going to show you how Wong made it and how we can make it, but faster, okay? And so Wong's theorem, our Ramanujan type identities, all come from equation 2. They come from cubic polynomials. That just means this is a polynomial, and a cubic means it has an x to power 3 at the front, okay? And so from this cubic, if we have the roots or the answers being alpha, beta, gamma, by this theorem, we have the cube roots of alpha, beta, gamma are equal to this right-hand side. And this t is really where the difficulties lie. All right, we need to figure out this t. And t is the only real root of the what we call the associated Ramanujan equation, which is number 4 here. Okay, so to get t, we have to solve this entire kind of new problem here, number 4. All right, and so what Wong does to get his t is you're given alpha, beta, gamma. They're these things up here. Okay, and you have to calculate what he calls sigma alpha beta, and alpha beta gamma. All right, and really, when you calculate them, when you just plug them in here, we get this that I'm boxing. All right, with this sine pi over 9, sine 2 pi over 9, sine 14 pi over 9. This apparently is equal to 0. Okay, and then we get an even worse looking identity with this trig functions. Right now they have them being multiplied, and apparently this is equal to negative 3 over 4. Now, you can ask most actual professional mathematicians, and they would have a hard time finding this trig identity, okay? This is not easy. Even like professors would have difficulty, right? This one's 0, and it's still, they'd give them a hard time. They might have to look it up. They might have to read some papers, okay? And this is really the shortcoming of Wong's style, or Wong's proof, okay? Because it doesn't even end there. We need to calculate alpha over beta, which is negative 3, and beta over alpha, which goes to 0, right? But again, seeing that this bottom chunk of the equation, seeing that that's equal to 0 is very difficult. And so we do all of this work to get a 9, which will plug into the formula, which gets us this red 3. Okay, so all of the last two slides, these two slides, were to get this red 3, which is, kind of anticlimactic, right? Like, it's kind of disappointing. But then we get t, which is equal to this, which we plug in here in this red part, right? And so we get our new Ramanujan type identity. And so that's great. We have a new approach that's based on the work of Liao, Sol, and Xu, and also Chen. So we're kind of combining these two results, really to try and find t better or faster. And so we have this theorem here, where we have an arbitrary cubic, okay, and the roots are alpha, beta, gamma. But by using what we call the Vieta formulas, these are very well known, very old. The Vieta formulas tell us that sigma alpha is actually just negative b over a. And this is c over a and negative d over a. Which means we can get these quantities by just looking at the original cubic. Okay, which is a big deal, because that means we avoid calculations like this, right? In Wong's proof, we had to find all of these trig identities and sum them together, and then we take the fractions of them and sum them together, and it was really quite difficult, right? I'm pretty sure no one looking at this slide can follow the trig identities, at least fast. And so our new approach is that if you're given this f of x up here, all right, and the associated Ramanujan equation, here I just put p and t equal to this for space purposes, we get that t automatically is this thing, okay, equation 5. And we notice that we have a's and b's, and then this delta here, again, this is just to save some space. Delta is this. And again, it might look kind of bad, but the beauty or the good part is that this just uses a and b, right? There's no other letters here. There's no alpha, beta, gamma, which, right, those were the trig numbers, okay? This is just a and b, which is up front. So if I were to do Wong's Ramanujan type identity, we have this equation. This is what gets us this cubic, his Ramanujan type identity. Here we see that a is 0 because there's no x squared. B is negative cube root of 9 because that's the number right here. All right. If we plug this into the associated Ramanujan equation, we have by our theorem this delta squared. You just plug in a and b. A is 0, so it's not even that difficult. You're going to get a 9. You square root both of them, and then you get the red 3 that I was talking about. And then you just plug it in, and it falls out, okay? So dramatically, I just cut down his proof by like an entire 2 slides. And the big improvement is that we no longer need to know these extremely difficult trigonometric identities, okay? Right, we get this right-hand side right away just by plugging into our new formula. And the left-hand side is just automatic, right? It's just the roots that we already know. Okay, so here is the short proof of this Ramanujan type identity. And so this paper just kind of is a direct improvement, right, of Wong's result to get new Ramanujan type identities. So all we need is to know the roots of the cubic polynomial and then make our associated Ramanujan type identity, and then we can just use the coefficients to plug into our new formula and get the answer, okay? That's pretty much it for my talk. Here are some references. Thank you so much, and goodbye.